Thank you. Good day, everyone. I am Sarah Asad Abbas, an associate professor of electrical and computer engineering at Northeastern University, and also the associate director of PAIR Initiative. And today, with my PhD student, Jiangyu Bai, we will share how we think about visual intelligence in the era of physical AI through our work on grounding visual AI models in real-world physics. Um, at my research lab, Augmented Cognition Lab, which is part of the PAIR initiative that Professor Ye just introduced, we focus on building systems that can perceive, reason, and act in the physical world, not just recognizing pattern in the data. But many of this domain and some of the example that you see here that we care about, such as human monitoring from infants to elderly, autonomous navigation in harsh weather conditions, animal monitoring, defense application. They are the domain that they are fundamentally small data regimes in which data is limited or expensive and sometimes even impossible or unethical to collect at a scale. So instead of asking how much data can we collect, we ask how much physical structure, especially in our case, motion and dynamics, can we extract from the data we already have. And this shift is actually essential for physical AI because we want to go from scaling data to understanding how the world evolved. But physical AI is not just a machine learning or computer vision problem. To model the real world, we need real world knowledge. And this comes from clinician, roboticists, ecologists, industry partner, or even a policymaker. And because the intelligence in the physical world, it's constrained by physics, context, and human impact. So through PAIR, we have been fortunate enough to closely collaborate with across healthcare, robotics, government, and industry, as Dr. Ye mentioned, to define meaningful problems. We also access real-world environments and data and ground our models in physical reality. So the ecosystem, this ecosystem allows us to make data efficient real world AI possible, especially through our PAIR initiative. But today I would like to concentrate on few topics to see that how we can go from the computer vision towards physical AI, and I think some of these topics would be very much of interest to many of the Voxel 51 followers. So I would like to start with the topic of why video AI needs a rethink and why scaling data and parameter alone leads to model that can reproduce appearance very well, but they fail to reason about the context. Then I'll present motion as a core representation that we have been working on and how motion as a signal provide a low dimensional interpretable bridge between pixels and physics. And that leads to enabling data efficient zero prompt reasoning. And Jianyu would go and talk about that how physics grounded video generation can lead to a learnable world model that capture how the world evolves rather than just how the world looks like. And hopefully by the end, we can envision building systems that learn from motion, reason over future state, and operate safety in the real world environment. And the main takeaway from this talk would be how could we go from scaling data to modeling dynamics in the physical world? So the next part is the work that is led by my PhD student Sheida Moazzi on why video AI needs a rethink. Her hypothesis is centered around this idea of that real world intelligence means predicting how the world evolves, not just describing what it looks like. And as we all know, scaling works. We have seen all of this success in the AI model, but we know that it's also worked mostly for recall. Uh, our today's video model are very much impressive, but they are impressive narrators. I mean, they imitate the appearance as we ask them to generate very well, but struggle with motion, causality, and physical change. And I'm going to show you some example of that very quickly coming up. And the reason is that the most video model are still treat videos as a bag of frames and language priors. And dynamics in them are fragmented, motion is aggregated and not reason over. So the real question here isn't it how much should we scale to make a better model, especially in the video domain, but it is what we should scale, data volume or structural understanding. And we propose that motion, not more data, should be the foundation of visual intelligence because if we model motion explicitly, we can predict how the world evolves, not just what it looks like. And that's the beginning of the world modeling that is also one of the deliverable and one of the goal of the PEAR initiative. Now let's start with a simple example. Look at this example. This is in this example, as you saw, an apple is tossed upward into a tree. But the model here, Gemini 2.5 Pro, which is the state of the art, confidently says, in red, an apple falls from the branch into Newton's hand. Why? Because many of the video language model, they are suffering from these two failure modes. The first one is the static cue dominance. The tree and apple here, as you see, are dominant the attention of this model, and the subtle upward motion is completely ignored. Also, the prior-driven temporal hallucination, that the model completes the most likely story that it memorized, had seen in the textbook. And I want to emphasize that if a model can perform well on a benchmark without reliably perceiving the pixel dynamics or even watching the video from the beginning to end, it isn't understanding the video. It's actually remembering a story. So the idea is that many of these models, they are not tracking pixel, but they are completing a script. And I'm not going to stop only here. I mean, this is a very famous Newton graders that grader school, they could see this doesn't follow the physics. And in this Sora generated video, the momentum transfer fails because if you look at that, the rightmost ball stays completely stationary. But the model, both model, actually we tested on several models, Gemini and GPT-4o, confidently describe it as a canonical story of the outward swing of the ball. And they said that the physics is completely it's preserved. And the output, if you could read that, a very fluent textbook-like explanation. And this is actually the very prime example of prior-driven temporal hallucination. When here the visual evidence contradict with the word knowledge through the only text understanding, the model completely abandons what is happening in the video from the trajectory, from the motion, from the dynamics, and complete the most likely story that it should be. And what is the shift that is needed happen is that the video is not frame, it's a transformation. And if we keep treating video and static images, we keep building very nice but articulate narrators instead of physical reasoning. And that's the reason that we propose that fundamental units of the video understanding must be motion, not only images. And when motion becomes the core representation, the model stop describing only appearance and start modeling how the world evolves. And that shift from appearance to evolution is one of the foundation of the physical AI. Although that part is about perceiving the world, but we have to perceive and recentering perceiving the world on the pixel dynamics rather than only pixel appearances. And that's the part that I would like to go and talk about very briefly on how we bring motion as a core representation. This work is led with my other PhD student, Bishoy Galoa, which the work talks about that how we move from a static frame now, and a static frame, actually a static frame aggregation to dynamic world understanding. And motion here is what's connect this raw pixel to physical structure. And it gives us continuity, it gives us interaction as well as causality. And Bishoy hypothesis here is that once motion is primary, reasoning no longer needs to be prompt driven, and we can move towards the zero prompt dynamic driven understanding of the world. And here, for word is captured in our work, is captured through videos, but I could imagine that it can go beyond the video. And the system can start extracting and discovering a structure without waiting for the user instruction and what prompt is happening. And that's behind the idea behind our track and caption and emotion TCAM that combines precise motion tracking with semantic grounding. And that all happen automatically without waiting for a query. And here, again, instead of asking what should I search for, waiting for the user, somebody, an oracle to give us to start looking for that specific motion movement, we ask what is changing, what interaction matters, and that's a shift from retrieval to motion grounded discovery. The TCAM has three main parts: motion centric design, query free discovery, and multi expression grounding. And together, this principle allows us to get closer to true dynamic word understanding, and where the semantic emerge from motion, not just the text prompt. And hopefully we are going away from those two failure modes of just static appearance and dominance of them, and also temporal hallucination because of the word model that is happening within only our language models. Briefly, very briefly, I'm going to go through how TCAM structure looks like. All of the code data as well as the paper related to that is available, and you can contact me or Jimmy afterwards, and you can get access to those. So the main idea here is that when the video comes, we can apply tracking the motion inside that. It can be through the point tracking we use here for this version, Code Tracker 3, to extract the motion trajectory, but it can be any tracker. We have also more recent model that can be applied from one view, several view. The next part is this trajectory, when in the past was completely ignored, then can create motion descriptor. And here we align them with clip space, 512 dimension. The vision part of that, the vision embedding through the vision transformer can be frozen. You can open them, as well as the text bank as well. For this version, again, we have them frozen, but based on the specific application that you are using from one domain to another domain, you can open up this text bank and start retraining that. And then what here we added on top of everything is this multi-head attention mechanism that allows to find the text and motion relevance and track them for a spatial grounding. Then for the discovery, based on the text, motion, and visual appearance, the similarity-based retrieval happen on several expressions that happening rather than just focusing on one thing. I mean, the word is not one important event that happen. The word, several events may happen simultaneously. So this allows us to extract them all at the same time. And how to train that, we use contrastive learning here, and through a semi-supervision we can actually, and also self-supervision here, we can do ranking of the positive pairs from the trajectory, description, and where they are happening in the video. So you have a video, and then you can start actually saying what's happening inside the video, and also ground them on where that specific event is happening. Here I'm showing several videos. Actually, it's important to pay attention that these models can look at several things even with their similar appearance, because the motion is different, and caption them. We can go through the occlusion, camouflage, and track the motion, because every object here have their own motion signature, and they can be tracked, and then we can see what's happening throughout, even when the camera movement happening and we lost the object and subject. Also, many of the event, the word expression is not always one thing is dynamic, one thing is static. You may have the combination of them, and we should be able to track them and say that which one is doing what. So that is the beginning, the main goal of the video understanding. So far, I talk about that what is wrong, what we are doing now for video understanding as a means of understanding the world, how we bring dynamic and motion as part of that. And now I would like to invite my PhD student, Jianyu Bai, to talk about how we can have this motion awareness as part of the video generation and goes towards the dynamic word modeling. Jianyu, let me stop sharing now.
I hope everyone can see this. Thank you, Professor. Now today, I would like to show you how we move from appearance-based video generation into physics-grounded video reasoning. This is where MoReGen, our multi-agent motion reasoning engine, comes in. Instead of producing pixels directly from text, like most generative models, MoReGen does something fundamentally different. It bridges physics reasoning and video generation via simulation code. Before we show MoReGen in its action, let's look at why existing models struggle. Modern text-to-video systems, including Kling, VanView, and others, produces beautiful visuals, but when you look at them closely, the physics breaks. For example, divers dive without proper trajectories. Newton's cradle doesn't conserve momentum, as we just see, and ball slides uphill instead of downhill, clipped through objects like implausible or bounce through in different ways. These phenomena happen because these models are purely data-driven. They mimic patterns from training data, not the rules that governs the physics world. So when they encounter a scene outside their training distribution, the physics collapse. As we can see, today's generative models looks impressive, but fails the moment physics matters. So the natural question becomes, how can we bring real-world physics into visual AI models without relying on massive data? Our answer is that to use simulations instead of memorization. By grounding video generations in Newtonian physics mechanics and structured code simulation, we ensure the motion reflects real-world causes and effect. Simulation gives us a way to encode real-world dynamics directly into a generation process. And to start building that foundation, we turn to the most fundamental frameworks we have, Newtonian physics. Why do we start with Newtonian physics? Because it's the foundation of how objects moves in our everyday life. And before AI can reason, it must respect the laws of force, motion, and energy. By grounding models in these rules and supervised LLM agents with both visual and physics alignment, we create systems that don't just generate pixels, they understand the physics relationships behind them. Our goal is to bring classical physics intuition back into modern AI architectures, which brings us to the full MoReGen pipeline. Here, this is the full pipeline. It starts with text parsing, understanding the user's intent, and extracting the physics requirements. Then we have the code writer agent that generates executable simulation code. The physics engine runs these simulation codes, producing a grounded trajectory. Finally, our evaluator analyzes the quality, physics validity, and semantic alignment to user intention and feeds that all back into the loop. This multi-agent iterative refinement process eliminates the need for massive video datasets. Instead, we use LLMs and physics engines to generate physically consistent motion. Of course, generating a motion is only half the story. We also need to know if it's correct. That's why MoReGen relies on a multi-agent feedback and iterative refinement system, which I will walk you through next. Let's look at this rustic initial generation. To ensure the correctness, MoReGen uses three evaluators. The vision language evaluator that checks the visual quality. It tells us that the video is low in quality, low in resolution, and way too short for our purpose. The physics evaluator that tells us the animation we see violates physics rules. The ball indeed intersected with a plank, which is impossible in real world. It checks the motion trajectories and other physics phenomena for any violations. Then we have our intent evaluator with visual language models and large language models that ensures the video matches the user prompt. In this slope and plank scene shown, we conclude that previous generations violated laws of motion and the objects intersected unnaturally. Our physics evaluation identifies these issues directly from trajectories rather than appearance. These evaluators helps us identify issues. However, we still need a way to quantify physics accuracy precisely, especially when it comes to qualitatively and quantitatively evaluating. That's where our new set of metrics suite, the MoRe Metrics, comes in. Traditional metrics like FVD, video distance, and FID, image distance, only measures appearance similarity. They compare directly from data distribution to other distributions and give us a score that represents how well the appearances reconstruct itself. They do not care if a ball accelerates incorrectly or violates momentum conservation. So we introduce MoRe Metrics, which directly compares trajectory using grounded point tracking, dynamic time wrapping, and Procutus analysis. Take a look at this example. Now, this is a prompt with a lot of math and physics relations. And see how our model constructs this prompt perfectly to the reference ground truth. And also observe how data-driven generative models fails to replicate physics phenomenons. Observe how point tracking creates the object trajectory. We use this trajectory to enable rigorous quantitative evaluation of physics correctness, not just visual realism. And to support these new metrics and to provide a unified benchmark, we built a dedicated dataset. And now let me introduce MoReSet. MoReSet is a Newtonian physics benchmark containing over 1,000 videos across 9 categories of physics. These categories are gravity, acceleration, collision, oscillation, momentum, buoyancy, inertia, pendulum motion, and pulley mechanics. Out of which, there's 1,200 Blender-generated simulations with structured physical specifications, 75 real-world lab videos with detailed human annotations, and each sample includes pixel-level trajectories enabling evaluation of both appearances and motion correctness. Now, let's take a look on this benchmark how our model compares against other big names. Here, you can see MoReGen compared to major commercial and research models on a very simple scene of Newton's cradle. Many existing systems generated visually appealing scenes, even including the reflection on the steel balls, but they break physics. Objects float, they bounce incorrectly, or behave unpredictably. MoReGen's result aligns closely with ground truth motion because it reasons through simulation and it produces videos that actually follows physics rules described in the text prompt. Seeing these comparisons naturally raises a question. Can high-fidelity visual models benefit from physics-accurate motion guidance? Our next slides explore what happens when we actually try to do that. And actually, this is one of the most common suggestions when we hear whenever someone sees MoReGen. They often say, well, if MoReGen gives you great physics but simple visuals, why not just use your physics-correct motion as conditioning for a high-fidelity generative model? On paper, that sounds totally reasonable, but in practice, that it is not a simple task. Even when we provide correct motion field, most existing models still fail, and the reason is fundamental. They do not comprehend how motion integrates with visuals. They treat motion as a texture, not as a physics constraint. The physics collapse again in these scenes. What this shows is that physics can't be just added to a top of a video model. It has to be built into the reasoning process itself. even you see here, the state-of-the-art models like NVIDIA's Cosmos 2.5 can struggle. Again, because most models fundamentally lacked explicit motion reasoning. They assume physics will emerge from visual tokens, and as we repeatedly shown, it does not. Producing visually consistent videos when it comes to physics, even in the simpler scenes, still breaks. And one of the other more interesting directions we explored in this is to the projection from 2D to 3D, representing by the task of novel view synthesis. Of course, you might notice one weaknesses of our model is that it is entirely 2D, but we can still see that these models struggle due to the lack of the understanding of 3D scenes and the underlying spatial and physics constraints of the scene. These few failed tasks pushes us from video generation towards world modeling, which is what we are doing at the moment in pair. By integrating reinforcement learning and physics critics agents, our next step of MoReGen does not just reproduce the past, it predicts future states. The model learns to adjust simulations dynamically, generating physics-accurate trajectories that evolve according to real-world dynamics. This brings us closer to AI systems that can reason, plan, and act safely in real-world environments. We are very excited for this future, and I'm not sure if Sarah, you have more comments to make.
Yeah, I just
This
wanted to
concludes my
finish the
part of the
last.
presentation.
Yes, let me get the last talk to how we look forward. I mean, just a couple of slides. Going back. Continue to share. So looking forward, I mean, thank you, Jean, for presenting. We wanted to say that as part of the pair and also the focus of my lab on the small data, we want to see that if the scale gave us the perception, structure would give us understanding, and how we can go from motion to intelligence by building perception, reasoning, and action on their small data condition, and grounding these model into the dynamics that guided by physics and a scalable beyond the scale and beyond the data that you have. This is very important because in the physical world, only a very few examples and domain you have the data that is required for the model and the huge model parameters that you have. And I would like to end that this goes back again to the vision that we have for pair. So how we learn from and model the real world data, which it is very in a very small data regimen. Reasoning within the word, what we use for reasoning, that reasoning cannot be afterthought. Zhang, you showed that. We cannot just say, let's have the best video model that can generate all of the pixels, but let's then overlay the dynamics on that. It's not going to work. We have to go back to the whiteboard, blackboard, and then start coming up what are the representation that we can use. And then giving that to the people that they are acting in the real world, and then providing that to the interdisciplinary research work. And I want to also invite everybody to the third CV for a small workshop with the theme this year on beyond the scale towards data efficient, dynamically aware video intelligence. This workshop is going to be as part of the CVPR on June 3rd or 4th. I mean, the date is not assigned yet, but this has been organized with several of my PhD students and many of the colleagues at Northeastern and beyond, as well as the collaboration with Voxel 51, 12 Labs, Amazon, Microsoft, and NVIDIA as well. So the paper submission time has passed, but we have a challenge competition with the great prize that would be posted very soon. Also, recently, Northeastern released two sections of the machine learning with a small data on Coursera. It should be free or just very low cost, that talks about how we can bring machine learning to a small data domain. What are the challenges? What is needed? And these two courses, the part 1 and part 2, is also available, and through the experiential digital global education. And thanks to Bishop, my PhD student, that helped me to put that out there. And I mentioned some of our PhD students as part of that, but this work cannot be done without the help of all of the PhD, master student, postdocs, and even undergrad in the lab. And thank you, everyone. I look forward to stay connected and send me and my lab members questions, and hopefully we'll be in touch through pair as well.